Good day, everyone. So for today, we're now going to continue with some partitions about vector spaces, and now we're going to discuss subspaces. Subspaces of vector spaces. For the objectives, we're going to determine whether a subset W of the vector space V is a subspace of V. So if we are going to consider a vector space, this is a vector space V. We are going to consider a subspace some vectors under V that forms a vector space in itself. Definition. A non-empty set W of a vector space V is a subspace of V when W is a vector space under the operations of addition and scalar multiplication defined in V. So for this one, we are going to know that W is a subspace if it is a component, it is part of V, which is still a vector space in itself. Show that the set W equal to x1, 0, x3, where x1 and x3 are real numbers, is a subspace of R³ with the standard operations. Initially, we set W is non-empty because it contains the 0 vector. So 0, 0, 0. So it is a non-empty set. Now, what we are going to do next is to check whether it is closed under vector addition and scalar multiplication. So we have a vector in R³ such that x2 is equal to 0. So it is the set of all vectors in R³ wherein the second component is 0. We are going to check that. So it would be a vector in this plane. So graphically, the set W can be interpreted as the xz plane as shown in the figure. The set W is closed under addition because the sum of any two vectors in the xz plane must also lie on the xz plane. That is, if we have x1, 0, x3, and y1, 0, y3, then the sum would be x1, y1, 0 plus 0 is 0, x3 plus y3 is x3 plus y3, which is also in W. So basically, if you're going to add two vectors in R³ that satisfies the given condition for that subspace where the second element is 0, the sum is a vector in R³ wherein the second element is still 0. Similarly, if you're going to multiply this by a constant, so constant times x1, 0, x3, so that would be cx1, 0, and cx3. Observe that the second element is 0, so it still follows the condition for that subspace. Hence, it is non-empty, it is closed under addition, it is closed under scalar multiplication, therefore, it is a subspace of V. So for the test of subspaces, if W is a non-empty subset, so first we check that it is a non-empty subset of a vector space V, then W is a subspace of V if and only if the two closure conditions are listed below hold. First, if U and V are in W, then U plus V is in W. If U is in W and C is any scalar, then CU is in W. So this is closure under vector addition, and this is closure under scalar multiplication. Another example. Let W be the set of singular matrices of order 2. Show that W is not a subspace of M22 with the standard operation. By test for a subspace theorem, to show that a subset W is not a subspace, show that W is empty. W is not closed under addition, or W is not closed under scalar multiplication. So let us consider this vector. In this example, W is non-empty and closed under scalar multiplication, but is not closed under addition. To see this, let A and B be equal to A equal to 1, 0, 0, 0 and B equal to 0, 0, 0, 1. If you're going to add this, so A plus B, the sum of A plus B is 1, 0, 0, 1. But this is non-singular. There is an inverse for this identity matrix. Then A and B are both singular or non-invertible. But their sum, if you're going to add A and B, we will be having 1, 0, 0, 1. Take note that A is singular. There's no inverse for A because it is 1, 0, 0, 0. While B is 0, 0, 0, 1. So it is also singular. So, but take note that their sum 1, 0, 0, 1 is invertible. There is an inverse for the identity matrix, which is the identity matrix itself. So W is not closed under addition because the sum is not singular. And by test for subspace theorem, W is not a subspace of M22. So therefore, this is not a subspace. So a singular set is, the set of singular square matrices is not a subspace of M22. The intersection of two subspaces is a subspace. So if V and W are both subspaces of the vector space U. So if this is the vector space U, if V and W are both subspaces, the region of intersection is also a subspace of U. Subspaces of R raised to N. R raised to N is a convenient source for examples of vector spaces. So the reminder for this section is devoted to looking at subspaces of R raised to N. Determine whether each subset is a subspace of R squared. So R squared is the set of vectors of coordinates x, y. So let us consider the set of points on the line x plus 2y is equal to 0. That would be, we can have x to be equal to negative 2y and y is equal to y. So this is your vector. Negative 2y, y. This is for letter A. For letter B, x plus 2y is equal to 1. So we can have x is equal to negative 2y plus 1. And for the second component, it is y. So for our solution for the first one, solving for x, a point in R squared is on the line x plus 2y equal to 0 and it is of the form negative 2t, t, where t is any real number. So negative 2t, t. If written in parametric form, we have negative 2t and then t. While for the second one, negative 2t plus 1 and then t. To show that this set is closed under addition, so if we're going to add negative 2t1, t1 to another vector under that set, negative 2 sub t2, t sub 2, if you're going to add that, negative 2t1, t1, negative 2t2, t2, so that would give us negative 2, t1 plus t2, t1 plus t2. If we're going to let t1 plus t2 to be t3, you're going to observe that that would be negative 2 times t3. So observe that this is just negative twice of the second component, which is the condition for that subspace. So in a similar way, you can also show that the set is closed under scalar multiplication. So this is a subspace under R squared. While for the second one, this subset of R squared is not a subspace of R squared because every subspace must contain the zero vector 0, 0. So one clue of determining whether it is a subspace is that it should contain the zero vector. It should contain the identity element, which is not on the line x plus 2y equal to 1. But if we want, we can also check negative 2t plus 1 t. Now let's have another vector, negative 2k plus 1 k. If you're going to add this, it would be t plus k. And then this would be negative 2t plus 2 minus 2k. So observe that this is negative 2 times t plus k plus 2. So it is not of the form negative 2 times t plus k plus 1. So therefore, this is not the same. So it is not a subspace. See you for the next video.